So you know it's getting kind of, the semester can get confusing, and when I start to put where do we need to pick up Monday, because I'm like, otherwise it's hard to find after 3 days left sometimes. But we talked about different definitions of acids and bases, and we're sticking with the Bronsted-Lowry definition, where acids donate a proton, meaning an H+, and bases accept a proton. Now, this actually, though, can you see where if something generates or donates an OH minus, can you see where that accepts a proton? Does that make sense? The OH minus accepts a proton. So it creates a basic situation. It is a base if it can provide 1 mole, at least, of the hydroxide ion. And of the definitions we talked about, I don't know, maybe it was Arrhenius definition, but actually this was the definition. So what works out well is a salt, which is an ionic compound, where the anion is the hydroxide ion. Okay. Sodium hydroxide, for example, will ionize or dissociate completely. We know that because there's a one-way arrow. It's none of this insoluble NaOH. It dissolves entirely. And this is where, for every 1 mole you dissolve, you'll get 1 mole of the hydroxide ion. Perfect. It's what we call a strong base. And you can start to get used to these, and I'll kind of have to go back and apply them to the acids we've already talked about. But SB is strong base. Okay, sodium hydroxide is an example of strong base. Calcium hydroxide also dissolves entirely, one-way arrow, and it is also a strong base. And notice, don't let this throw you off, that you get 2 moles of hydroxide for every 1 mole of the salt that you dissolve. Here's an example of a strong base, and it doesn't necessarily have the hydroxide ion in its formula. All it needs to do is to react with water to accept a proton from water, and if you take H2O and you accept the proton, guess what you have left? Hydroxide. So in accepting a proton, it forms a hydroxide ion. An example of this, and you're going to run into this maybe in your problems, is this is the F-oxide anion. So we have a carbon chain with 2 carbons that looks like this. Actually, F-oxide is ethanol without a hydrogen. Okay? So we have ethanol over there. Here's F-oxide. What does it do? Well, it can tend to accept a proton from a neutral water molecule, minding its own business. And in doing so, it creates that hydroxide ion. So F-oxide is another example of a strong base. Okay. So here we talked about strong acids. I guess there's 6 of them. And I know no one likes to memorize things, but I would memorize these things. Just like I would memorize, that for water, the density is 1.00 grams per milliliter, at 4 degrees Celsius. Things that you've already had to memorize here. So these are strong acids. Guess what we use for strong acids? SA. And these are strong bases. Okay. Now all of these are strong bases, not like the F-oxide anion, just donating a hydroxide group. All right. But the cool chemistry isn't in the strong acids and the strong bases. The cool or the interesting kind of finessing life sort of situations are in their weak counterparts. So weak bases. Guess what we use for weak base? WB. We talked about weak acids on Friday. Weak bases then. We're going to use a 2-way arrow. Okay? They do produce an excess of the hydroxide ion, but only to a certain extent. Now, to kind of have that all make sense, I want to talk about this. This is the deprotonation of water. So here you see your water molecule. B, remember, is some generic thing. It's not boron. B is the thing that came from your HB, actually. We have a negatively charged, looks like it's just itching to accept a proton. So this actually is our weak base, our base. Okay, the water molecule. On the product side, not so surprising then. In equilibrium, you're going to see your HB, and the water molecule without an H plus is a hydroxide ion. This is your OH minus. So basically, this is H2O plus B minus in equilibrium, form HB plus OH minus. That's it. So this is your weak base. And we said that actually the thing that provides the proton, a proton donor, is your acid, weak acid. And then honestly, if we were going to go, that's going this way. But what if we go this way from right back to left again? Does this make sense? That your HB is actually going to be your weak acid, proton donor. And your OH minus, actually that's not going to be, that's going to be, I'm going to put in an SB. It's a base, it's a proton acceptor, and it's a strong base. I think instead of a weak acid, that's probably, I'm going to go ahead and, yeah, I'll leave it that way. But you need to kind of get used to that whole going from left to right and going from right back to left again. It's a whole picture sort of thing. Just like it was with the acids. Okay. So yeah, we end up with an equilibrium here. And the cool thing we know about equilibria, we learned from Unit 3, is we can make equilibrium constant expressions. And I said, and I growl at it all the time, we had a Ka for the ionization of a weak acid. And here we actually have a Kb. So for a weak base, hydrolyzing or taking a proton from a water molecule to make Hb and OH minus, if we were going to take these things and put them in equilibrium constant expression, in the numerator we would have the molar concentration of Hb, also the numerator, the molar concentration of OH. Now these are all raised to the first power because according to this balance equation, the stoichiometric coefficients are 1. If they were not 1, I would have to raise them to that power. In the denominator, we have the reactants, which remember the liquid water does not show up, but we have the molar concentration of the B minus, and that was our weak base. Okay. And then this is from the back of your textbook. So these are some weak bases. Here are KBs. We have a lot more weak acids than weak bases. Okay. So if given an option, a substance that's a stronger acid than water will serve as the proton donor if it's in water, and water will accept the proton it gives up. So this is kind of what we talked about on Friday, where we have, this is the weak acid, I'll put WA, or my HB. And then, so this is going to be my, I'll just put B for base. I don't know whether to put weak or strong. That's my B for base. It's going to accept a proton. You can see it on the other side, accepting a proton. Okay. So, this will be the case if your Ka for your weak acid is greater than the Ka for water. We can do kind of a similar thing with regard to bases. A substance that's a stronger base than water will serve as the proton acceptor. In that case, water will serve as the proton donor, just like we saw then this afternoon. I use the word abscond, where your weak base absconds onto, it deprotonates a water, or excuse me, deprotonates a water molecule, taking a hydrogen and leaving the hydroxide ion. So this will be the case if the Kb for our weak base is stronger or greater than the Kb for water. That table in the cups. I thought I did. Okay. So now to finish up, just kind of a few terms. Mono means one. So monoprotic means an acid that will kick off only one proton. Polyprotic means it has two or more protons that it can donate. Some are more obvious than others. So, like for instance, HCl, it can only donate one proton. H2SO4 is an example of a polyprotic acid. And I think we're probably going to pick on H2SO4. The first hydrogen kicks off entirely, and that second hydrogen kind of lags behind. And it will be in equilibrium. Then another term, not related to monoprotic or polyprotic, is amphiprotic. Amphiprotic is really cool. It can actually be either an acid or a base. Okay, so it'll serve either as donating a proton, be an acid, or accepting a proton and be a base. And I'll kind of show you how that works. Oh, yeah. How does that work? Well, an example, the most common amphiprotic substance is water. We've seen today and in Friday's lecture where water can pick up a proton. Okay, it can act as a base, and it can also donate a proton, act as an acid. So there it is picking up a proton, and there it is donating the proton. So in this case, water is acting as a base. In this case, water is acting as an acid. Over here you have your weak acid. Over here you have your weak base. All right. So according to the leveling effect, it's kind of like we've been talking about, that the strongest acid that can exist in water is the hydronium ion, H3O+. The strongest base that can exist in water is the hydroxide ion, just because it is. And as I said, they're not scanned in, but I've got them out, and that's a good sign. But I only went up to part 5 of unit 4, so we'll see. I'm tired just thinking about it. They're fun, but hard to squeeze things in sometimes. So let's take a look at part 2, see if we can get all the way through it. We'll see. Okay. So, again, just to make sure, it's funny because I just did this in my chemistry and context. You guys are just neck and neck right now. But kind of build on what you already know about acids and bases. Really? Anybody see the marker? Paul. I'll go with green.
No, they did some walk with it. Huh?
Yeah, I made you walk with it. That's not gonna work. Oh. Right. I guess I need to throw that one away. Okay, so here's my pH continuum. pH 7 is neutral. And then we go from about, well, I think this textbook maybe says 1 or 0. 0 means this is very acidic, very acidic. You can have less than 0, and that's crazy acidic. Over here, it generally goes to, maxes out at 14, but you can have greater than 14, and this is very basic. So that's kind of what we're dealing with, pH. So actually, the P in pH means applying what we call the P function. And a P function is you take the log of something and then you multiply it by -1. So negative log of something, base 10, is applying a P function. So if we apply the P function to the hydrogen ion, we call it the pH. So pH is literally negative log of your hydrogen ion concentration. If you have your And if you have your calculators, go ahead and grab it, because we're going to be doing some things. I can relate. Oh, is that
every
your
day of
phone?
my life.
Oh, no.
Great, that's a good point.
It looks okay.
Pretty strong now.
Okay, so we're going to be dealing with pHs. We're also going to be dealing with pOHs. So, of course, you recognize in pOH, OH is the hydroxide ion concentration. So, brackets means molar concentration. So, to get the pOH, we just take the log of the molar concentration of the hydroxide ion times -1. That's it. Kas, right? Kas is the ionization constant for a weak acid. Well, sometimes we want to know what, or sometimes it's not the Ka value is given, but the pKa value. How did they get that? They took the log base 10 of the Ka and took it 10 to the -1. That's it. Okay, so here we have, this is called auto-ionization. I think I used that term on Friday, where water just splits. And does that do it? Yeah, it really does. Usually the hydrogen ion, the H plus, catches another water molecule and it forms the H3O plus. But this is what water is doing to a certain extent. Okay? But normal water, check this out. For every 1 mole of this, 1 molar, you get 1 molar of this. And wait, that doesn't make sense. But my point is that, yeah, for every how much this ionizes, this is what I was going to say. Put X here. You get an X and an X. Kind of like, we talked about molar solubility. Does that make sense? Well, the equilibrium constant expression for auto-ionization of water looks like this. Equilibrium constant expression. So it's always products divided by reactants, raised to stoichiometric coefficients. So here we have molar concentration of hydrogen ion, first power. Molar concentration of hydroxide ion, first power. Divided by nothing, because H2OL, right? It doesn't show up. So this is what we call the equilibrium constant expression for water, just doing its thing. Now there's a value for Kw that you're going to want to memorize. And here it is. At 25 degrees Celsius or so. Now, sometimes you'll see me, if you only need it to 2 sig figs, check this out. 1.0 times 10 to the minus 14th, right? 3 sig figs, 1.01 times 10 to the minus 14th. So, whatever, they all mean the same thing. So, that's your problem, not mine. But, do you guys see this? Where I had us put x's up here, so here we have an x, and an x is equal to, 1.008 times 10 to the minus 14th. Can you get to the value of x? Heck yeah. Just take the square root of that. Okay? So already you know in general, and it's all written on it, if you take the square root of 1.008, or actually the square root of 1.0 times 10 to the minus 14, you get 1.0 times 10 to the minus 7. And that at 25 degrees Celsius, if this is 25 degrees Celsius, that would be the molar concentration of my H plus, the molar concentration of my OH minus. So to a certain extent, it auto-ionizes. And what I'm describing, go ahead and tell you, is this. That's a neutral solution. And we'll kind of come back around to that. So auto-ionization. Like I said, usually instead of that naked H plus there, actually it's going to catch a ride with a water molecule, and instead of being H plus, it's going to be H3O plus, which I told you the other day means the same thing. H plus is equal to H3O plus. Okay. So let's take a look at this video. Hydronium and hydrogen ion are the same thing, but you're right, that's hydronium and hydroxide. Yep. Okay, so this is showing you the same thing, the auto-ionization of water resulting in the hydronium ion. So in this case, actually, one water molecule acts as the proton donor, and one water molecule acts as the proton acceptor. But the molar concentrations you're talking about in regular water, 1 times 10 to the minus 7th molar, that's pretty low. Okay, but it's there. So Kw, the auto ionization of water for any dilute aqueous solution. So actually it's the auto ionization of water, but let me add to that, okay? It's also for any water at 25 degrees Celsius. It's like it's an equilibrium. So if you add more H pluses, guess what? Your OH minuses are going to decrease until you get that same Kw, which I told you to memorize, 1.008 times 10 to the minus 14. That's the constant. And again, this says not just in pure water like I've been talking about, but in water that's acidic or water that's basic. You both blend together, you get the Kw. All right. So this is the P function of applying it to the hydrogen ion concentration. Looks like this. Now, I think we've played around with this. If I want to get to the hydrogen ion concentration, if I would take, how does this work? 10 raised to the pH, over here 10 raised to the negative log molar concentration of the hydrogen ion, this actually would boil out to be negative molar concentration of hydrogen ion. I think that's what it's down. Well, anyway, hold that thought. So that's pH, this is POH. There are times when you are given the pH and you want to come up with the hydrogen ion concentration. So forget mine, I'm going to erase it. So there are 3 things up here. Now the second thing is if you're given the pH and you want the hydrogen ion concentration, this is what you do. And guess what? How about the hydroxide ion concentration? It's 10 raised to the negative POH. So these are tools in your toolbox. Now remember the way my slides go in Chem 1 and Chem 2 is anytime you see this kind of box like that with a color, that can be a helpful tool. All right. So if we take the log of both sides, okay, the negative log of both sides, actually you're going to end up applying the P function basically. So we could take this and expand it out, and we could say that the pKw is equal to the pH plus the POH. Okay, it's mathematically the same thing. He's tired back there. You're making me tired. So, in the same vat of water, not only do you have the molar concentrations of the hydrogen ion and hydroxide ion, you will do a pKa, but the pH plus the POH for the same solution needs to be equal to your pKw. So help me out. Take your calculators and go ahead and pKw is equal to negative log of Kw, which is 1.008 times 10 to the negative 14th. So however you need to figure out to do it, I want you to take the log of 1.008 times 10 minus 14 and take that times minus 1. And what do you get?
I don't want to get it wrong, but I got 13.996.
Okay, 13.96. So rounded it to 2 decimals. Yep. Did you guys get 14.002? You see where that came from? 14.00. That's at 25 degrees Celsius. Did you get that?
I can't find the dang key for the X times 10.
Oh, there it is. There it is.
Oh, okay.
Yeah.
Okay, sorry. I shouldn't have more than one calculator, it confuses me, so.
Did you get it?
Yeah.
So that's pretty cool. So, you know, if you have a pH of 8, then basic. If you have pH of 8, that this is your solution, 8. pH is equal to 8, and your pH plus your pOH has to be equal to 14. Say we're at 20 degrees Celsius, 25 degrees Celsius. What's your pOH? pOH is equal to 6. That makes sense? Yeah. Because these added together has to give you your 14. Yep. You got it. All right. So Kw at 25 degrees Celsius is 1.008 times 10 minus 14. And again, you're going to see me with the coefficient go with 1.0, 1.00, 1.0, 1.01. And if we apply the P function to that, just now you guys told me your pKw is 14.00. So again with the box, right? At 25 degrees Celsius then, this is the relationship we have between the molar concentration of your hydrogen and your hydroxide ion and your pH and your pOH, assuming it's at 25 Celsius. Did you get it?
I did the KW at the top there,
Okay.
and it came up to maybe 13.
Okay.
What was I supposed to?
Getting close. We've got more coming up here too. Yeah, you've got more coming up here. So here's where I say the practical scale runs from about 0 to 14, with in the middle is 7. 7 is neutral. So, but we can have pHs of less than 0 and more than 14. Exclamation point. So let's watch this video. Oh, there's no sound to it. But it's, do you see where the molar concentration of your hydronium ion and your hydroxide ion has to, and I'll replay it, the product has to be 1 times 10 to the minus 14th. And you know the way that works is, in this case, the coefficients are all 1. But you're looking at the powers of 10 to combine be about 10 to the minus 14th. Now basic. The other thing in doing this, do you see where when we crossed into basic territory, past pH of 7, at that point, finally, our hydroxide ion concentration was greater than our hydronium ion. Here, our hydronium ion is greater. Last time, I promise. One goes up, the other goes down because the product is constant. All right. Again, different ways to look at the same thing. I've got some builds, I think, to kind of highlight. It's a very busy slide, but the way this works is if you go across any row, you can kind of see what's up. I picked on 8 up here. So pH of 8, your pOH is 6 because added together they're 14. So let's see what some of these builds do. So down here, again, this is just the same thing that we saw with the video. Here we have the molar concentration of the hydrogen ion, 0.1 or 10 to the minus first. The hydroxide must be way down there because multiplied together, you equal 10 to the minus 14. Getting more or less and less acidic. Here it's neutral. Okay. And by definition, something is acidic if it has more H pluses than OH minuses, and something is basic if that's changed. It has more OH minuses than H pluses. So here we go, the OH minuses are winning out. Okay. Here are just some things that you might have at home that are acidic, basic, are in our stomach, our gastric juices, very acidic. Vinegar, water, or carbonated water, 3.9, very acidic. Beer, urine, milk, blood, kind of get neutral. Seawater, baking soda, milk of magnesia, household ammonia, and 1 mole of NaOH. So the one you need to commit to memory is this one right here. And you can already see, what drives me nuts, It's rounded to 3 sig figs instead of 4 sig figs, but it's the same number, 25 degrees Celsius. So what happens to the KW as you get colder? Go up or down? Down, it decreases. And remember, KW is on the product side showing you, so basically your products are decreasing, right? So it's less autoionization at colder temperatures, more autoionization at warmer temperatures. Okay, so let's do a problem, shall we? This is kind of a really common thing where you're given a solution, information about the solution, and you're supposed to knock out 4 things. You're supposed to knock out the hydrogen ion concentration, the hydroxide ion concentration, the pH, and the pOH. And I think I'm probably going to show you a couple of different ways to work this. Okay. So we're going to do 2 problems. First one is a strong acid. Now, the strong acid part, meaning the strong in strong acid, means that it ionizes or breaks apart entirely. Okay? And then we're going to go change it up and go to a strong base and knock out those 4 quantities for both of those. So starting with the acid, 0.1 molar. Okay. What I would do is probably make sure I'm kind of thinking of this right. I would put 0.10 molar there, and of course that means 0.10 molar there, 0.10 molar there, and already I have one of 4 quantities I needed. So that's going to be my starting point. The hydrogen ion concentration, 0.10 moles per liter. Well, probably a common thing to do next, I think, would be to, so grab your calculators and apply the P function. So take the log, I usually think of, it's negative log of 0.1. Yep, so did you guys get 1? Yep, very good. Now, there's a little catch, there always is, right? We've been talking about how you report your answer correctly with regard to rounding. Here's the deal, and I think we've run into this before. So I clearly have 2 significant figures in the molarity. Now, to show 2 significant figures, I'm actually going to put them, to show 2 significant figures, they're the trailing digits after the decimals. So that's my 2 sig figs. Okay, cool. So right off the bat, what's your pOH? 13. 13, that's it. I'm going to show you, I'm going to, you rearrange this, it is 13, but if you rearrange pH plus pOH is equal to 14, then your pOH is equal to 14.00 minus pH. So your pOH is 14.00 minus 1.00. 13.00. Indeed. Okay. Cool. Well, so let's see. We got Is that 3 things now? 2 things. 3 things. Because we had our hydrogen ion, our pH, our POH. Now we need our hydroxide ion concentration. And I think what I end up doing here is, remember a few slides ago, I said to get your hydroxide ion concentration, you take 10 raised to your negative POH, negative POH. So go ahead and find your 10 key and raise it up to negative 13.00. Yeah? It's going to look weird. Did you get this? 1 point, and again 2 sig fig, so 1.0 times 10 to the minus 13. And that pink is kind of hard to see. Okay. This is the basic, and so what gets harder is just the weird number, odd numbers, and what makes it harder is a lot of times you have to do Chem 1 stuff on top of it, like, you have to come up with this molar concentration. But no, it does. This is it. And that one sheet, I know, the one sheet I gave you with how to get the pH and the H plus and the POH and the OH minus, that's helpful. So that's one approach. Let's try another approach. I probably would do that, but alternatively, we could go for the hydroxide ion concentration first. Remember we had the hydrogen ion concentration, that was at 0.10 molar. And we know at 25 degrees Celsius, this is the relationship between the hydrogen ion and the hydroxide ion. So rearranging it then, your hydroxide ion is equal to 1.0 or 1.008 times 10 to the minus 14 divided by your hydrogen ion, which again, this was given. That was that 0.10. We're working the same problem. And we should be able to do this in our head. But if you work that out, you're going to come up with 1.0 times 10 to the minus 13. My scribble's in the way. Or my scribble's in the way. And it should match, so both ways. So that we have hydrogen ion, hydroxide ion. Now we need to get the pH and the POH somehow. Okay. So yeah, on your calculator, go ahead and take the negative log of 1.0 times 10 to the minus 13, and you should get the POH. So negative log of 1 times 10 to the minus 13. And when you get negative log of 1 times 10 to the minus 13. Times minus 1. Negative 13 times minus 1 is 13. Yes, you got it. And it's that bare number that kind of throws us off. You got 13, and to show 2 sig figs, since it's a log function, we show them as numbers, digits, and they won't necessarily be 0, but digits, 2 digits after the decimal. And they should match. Every once in a while, I'll get, and it's a rounded, it has to be a rounding thing, I'll get slightly different answers, like, okay. Then the last one is the hydrogen ion concentration, which I guess I'm probably not going to do. Okay. All right, so base. Again, I think this is a good example of, let's make sure we're on the same page. If I have 0.0025 molar of that, what's the molarity of the barium plus 2? The same. because of stoichiometry. But what is the molarity of the hydroxide ion?
It's 0.005.
Yep. It's twice. Yep, you guys got it. You guys got it. And that's important. Don't let that throw you off. And that's one of our 4 quantities. So again, you have some options here.
Do you use like do the math, like the stoichiometry math to get to the moles?
In Chem 1, yes. In Chem 2, no. Probably not. I don't know if that's fair, but and to me, I like writing it under things. I'm like, okay, I can see that. So yeah, that's a good question. And you can see, I just said from stoichiometry.
Okay, so what is that total called? Because I'm getting mixed
What
up.
is what total called? That?
The OH.
The hydroxide ion concentration?
Okay.
Yeah, hydroxide. Yep. So, looks like what I did next, and I already showed you the answer here, but feel free to tap it into your calculator. So if you have the hydroxide ion, to get the POH now, you take negative log of 0.0050, giving 2 sig figs. I have to show 2 digits after the decimal.
Surprise, I got it.
We could go, I think I have a couple ways to show you. Let's see. One approach would be to go for the the pH next. The pH will be equal to 14.00 minus the POH. Yeah, and this one I'd have to tap in. So you're looking at 14.00 minus 2.30. So your pH is 11.70. And then, this is where we are a lot more familiar with pHs than POHs. But this is where I'm like, oh, I could buy that. 11.7. And then we still have a few quantity, let's see, I guess the last quantity, how are we going to get the hydrogen ion concentration?
OH equals whatever it is divided by.
So we could do I know this is what you're talking about. We could do the H plus is equal to 10 raised to the negative pH. Yep. So in this case, H plus is equal to 10 raised to the negative 11.70. So if you plug that in, 2 sig figs. Mean zero.
It's a
Me
negative.
too. 2.0 times 10 minus 12.
11.7, right? Negative 11.7.
Yeah. 10 raised to the negative 11.7.
I keep getting 1.16.
So,
Okay. Start with negative 11.7. Why is it going to be that?
negative.
Oh, okay.
We have to use this.
Oh, okay.
Closer. Wait, so she's got an XY key, so don't we just, is that what you guys are using, your XY key? X to the, or Y to the X?
10 to the X, or you can just do 10, a little caret.
Yeah.
It's just a caret.
I
Okay,
hate this pencil. I
raised
just
to
want to
the,
make
oh,
sure.
negative, this times a negative.
I'll negative 10 instead of?
Oh, 10 raised, sorry.
Yeah.
10, do the X to Y, and do 11.7, and then do negative.
Oh.
Gosh.
Thank you.
Yes.
Sorry.
That worked. Okay, so alternate approach. So we could go for the hydrogen ion concentration, rearranging, that's our Kw expression. So your H plus will equal to 1.0 times 10 minus 14 divided by your hydroxide ion. And we knew our hydroxide ion was 0.0050. So divide that out and you get the hydrogen ion concentration is 2 times 10 to the negative 12 moles per liter. And then what we know to get the pH is we have to take a negative log of that. So if you take the negative log of quantity 2.0 times 10 to the minus 12,
I'm trying to get down so I can keep up.
yeah, for sure.
Okay. And then plug it in?
Yep.
11.7.
Yay, 11.7. And 7.0 would be right because we have 2 sig figs there and we show 2 sig figs by the digit trailing the zero, trailing the decimal. All right. So this will be kind of what we've been talking about. Acidic means you have more H pluses than OH minuses. And in that case, that means your H plus is going to be greater than that tipping point, 1 times 10 minus 7. Your OH minuses will be less than, because multiplied together, they equal a constant amount. Your pH will be less than 7. Your pOH will be greater than 7. So it's nothing that we haven't been talking about. Basics, the other way around. You have more OH minuses than you do H pluses. That means your OH minus concentration will be greater than 1 times 10 minus 7. Your H pluses will be trailing that. And that means your pH will be greater than 7. Again, I'm much more, find my way around the pH scale more than the pOH scale, but your pOH will be less than 7. Neutral solution, they're equal. That will be your molar concentration, assuming at your 25 degrees Celsius. Remember, that was that's the square root of 1 times 10 to the minus 14. Your pH and pOH will both be 7. This is to kind of warn you that if you need a Ka value, and I was going to add to this. If you need a Ka and you're given the pKa, you can do this. Does that make sense? We're just applying the same pattern. If you're given the pKa, but you need the Ka, take 10 raised to the negative pKa, that will be the Ka. Okay? All right. So both parts 1 and 2 will be due on Wednesday.